In the previous lecture, we have discussed action angle variables, and actually the Hamilton-Jacobi theory provides the concept of two very important variables which are called action angle variables, and actually this idea is particularly utilized in solving the problem of periodic motion. And definitely you have studied in your course on classical mechanics in the chapter central force field Kepler's laws of planetary motion, and definitely you have an idea that there is actually three laws of planetary motion given by Kepler. The first law actually is known as the law of orbit, according to which every planet revolves around the sun in elliptical orbit, okay, having the sun at one of its foci. The second law is called actually the law of area. This law actually states that the aerial velocity of a planet is constant, or area swept out by any planet, the radius vector of any planet with respect to the sun is constant. Actually, the third law is known as law of period, which actually defines what will be the time period of or the frequency of the periodic motion of a planet. According to Kepler's third law, the time period of any planet is proportional to the 3/2 power of the semi-major axis of the elliptical orbit. So this third law is actually related to finding the time period or frequency of this elliptical motion of a planet. So today, in terms of the action angle variable, or you can say as an application of the concept of action angle variables, we are going to see this particular problem, which is called Kepler's problem, because action angle variable is used to find the frequency of periodic motion. So when you say that we are going to solve Kepler's problem using action angle variables, that means you have to prove Kepler's third law. Okay, so our basic aim in this lecture is to prove the Kepler's third law by the use of action angle variable. Actually, this is a very important problem and also very important for your examination. So let us see. As you know, a planet moves under this gravitational force of the sun, and gravitational force is a central force. So first of all, we will consider any particle, not a planet, moving in a central force field, and we will obtain the Lagrangian and Hamiltonian of that very particle, and after that we will apply the Hamilton-Jacobi theory to discuss this problem. So let us see. If you consider that there is a particle of mass m moving in a central force field, then its kinetic energy, if you denote it by the symbol capital T, that will be given in spherical polar coordinates r, theta and phi. In fact, motion in a central force field takes place in a plane, and here the two coordinates r and theta is sufficient to discuss the motion. But for getting the general result, I am not talking about that particular case, but I am talking in terms of all the three spherical polar coordinates r, theta and phi. So the expression for kinetic energy, that is given by 1 over 2m r dot square plus r square theta dot square plus r square sine square theta phi dot square. You know, here a dot symbol means time derivative. When you say r dot, that means dr by dt. And similarly, theta dot means d theta by dt, phi dot means d phi by dt. And I hope you have definitely an idea of this. Okay. In fact, this r dot is the radial velocity, r times theta dot is transverse velocity, and r sine theta phi dot is azimuthal velocity. So this is simply half m vr square plus v theta square plus v phi square. Okay. And as we are talking about the motion of the particle in central force field, where the potential is defined like this. This is minus k over r. Or you can say the force will be obeying the inverse square law. F will be proportional to 1 over r square, and potential energy is inversely proportional to r with minus sign because this force is attractive. Okay. Now, after knowing the expression for kinetic energy and potential energy of the particle moving in this central force field, now you can easily write the expression for Lagrangian of this particle. You know, Lagrangian is simply t minus v. And the expressions for t and v are defined here. So let us substitute those values, and then you will get L, which is m over 2 r dot square plus r square theta dot square plus r square sine square theta phi dot square, and minus v, but v is minus k over r, so minus minus will become plus, and that is plus k over r. Okay. Now, you know, from the definition of generalized momenta, you can find the three conjugate momentum conjugate to the coordinates r, theta and phi. The conjugate momentum of r, that will be denoted by PR, and you know this PR is defined as del L by del R dot, because in general you know that PK, which is the conjugate momentum of the coordinate QK, that is defined by del L by del QK dot. This is general definition, and such idea you have studied in the previous lecture of in my playlist in the very beginning. So PR is defined as del L by del R dot, and let us see this expression for L. When you will differentiate it partially with respect to R dot, then your result will be simply mr dot, because the derivative of r dot square will be 2r dot, and this 2 and that 2 will cancel out, and all other terms are independent of r dot, so their derivatives with respect to r dot will be 0. Similarly, p theta, which is the conjugate momentum of the coordinate theta, that will be del L by del theta dot, and when you will differentiate this expression for L, you will get mr square theta dot. And similarly, p phi, which is momentum conjugate to the coordinate phi, that is del L by del phi dot, and that will be equal to this much. Okay. So in this way we have defined the linear momentum conjugate to the generalized coordinates r, theta and phi. Now, you know the general definition of Hamiltonian of a system. Definitely, when you have studied earlier the Hamiltonian formulation of mechanics, then you study the generalized definition or the general definition of Hamiltonian. And what is this general definition? This is summation over k pk qk dot minus L. Okay. Now here we you can see that there are three components of momentum, PR, P theta and P phi. So instead of summation over K Pk Qk dot, you have to write PR times R dot plus P theta times theta dot plus P phi times phi dot. Okay. Here R, theta and phi are generalized coordinates. Okay. And R dot, theta dot, phi dot are generalized velocities, and minus L. Okay. Now let us substitute the value of this PR, P theta and P phi from here, which we have obtained earlier. And after substituting that value and also the value of Lagrangian, which we have defined here in this expression, you can obtain the expression for the Hamiltonian, and that will be 1 over 2m PR square plus P theta square R square plus P phi square R square sin square theta minus K over R. Okay. So this is the Hamiltonian of the particle moving in this central force field. Okay. Now, as you know, the action angle variable is applied by HJ theory, that is Hamilton-Jacobi theory, and you know the Hamilton-Jacobi equation can be obtained by replacing this Pk by del S by del Qk. When Pk, that is the kth component of momentum, is replaced by this del S by del Qk, where what is this S? This capital S, you know, this is called Hamilton's principal function. What is S? This is Hamilton's principal function. If you have watched the Hamilton-Jacobi theory earlier in my of my channel, definitely you can see there the complete concept of this Hamilton's principal function. If you have not watched those videos, I will suggest you must go through all those videos on Hamilton-Jacobi theory, because only then you can understand this action angle variable concept. Okay. So as Pk is equal to del S by del Qk. Okay. So on this basis you can say that PR is equal to del S by del R, P theta is del S by del theta, and P phi is equal to del S by del phi. Where what is S? You know, this S is Hamilton's principal function. Okay. Now let us replace this PR, P theta and P phi by this expression. So now the HJ equation in terms of S can be written by like this. This is 1 over 2m del S by del R whole square plus 1 over R square del S by del theta square plus 1 over R square sin square theta del S by del phi square, and minus K over R plus del S by del T equal to 0, because you know how we write the HJ equation. HJ equation is written as how? We write this equation in this manner. This is in fact H plus del S by del T equal to 0. This is HJ equation. So here instead of H, we have written this expression, you can see, and del S by del T that is. This is HJ equation. Now you can see only this last term, that is del S by del T, depends explicitly on time. Okay. So solution of this equation 2 may be found by using the method of variable separation. Variable separation method can be utilized to find its solution, and for this, first of all, we have to relate this S, which is Hamilton's principal function, with the Hamilton's characteristic function, which is denoted by the symbol W. And you know, this S is given by W minus alpha t. I have written it directly here because you have seen this in H.J. equation. When you will study H.J. equation, then you will find that S is equal to W minus alpha t. Here S, you can see, is a function of r, theta, phi, alpha and t, while W is not a function of t. T is constant here. Okay. In fact, in this equation, this alpha is actually the integration constant. Okay. So now if you will now find del S by del R, this will be equal to del W by del R, because the partial derivative of this last term alpha t with respect to R will be 0. Similarly, you can see del S by del theta, that will be also equal to del W by del theta, because this last term is not a function of theta. And del S by del phi, that will be equal to del W by del phi. So now H.J. equation you can write in terms of the Hamilton's characteristic function, that is W. Okay, and that simply we will replace this del S by del R by del W by del R, del S by del theta by del W by del theta, and del S by del phi by del W by del phi. And what will be del S by del t? You can see del S by del t will be what? Since W is not an explicit function of t, so its partial derivative with respect to t will be 0. And here the second term will be differentiated with respect to t, and that will be simply equal to minus alpha. Okay. So this equation, that is equation number 2, which is actually H.J. equation, will be now what? This will be 1 over 2m del W by del R whole square plus 1 over R square del W by del theta square plus 1 over R square sin theta del W by del phi square minus K over R and minus alpha equal to 0. I have brought that minus alpha in RHS, so I have written here alpha. Okay, I think we have clearly understand how we have expressed this H.J. equation in terms of the Hamilton's principal function, that is W. So that is characteristic function W. But when you have studied Hamilton-Jacobi theory, definitely you have seen that actually this alpha is nothing. This is for a conservative system. This alpha is recognized as the Hamiltonian of the system, and that Hamiltonian actually represents the total energy of the system if the system is conservative. Now here our particle is moving in a central force field, and you know central force is a conservative force. So definitely in this present case we are talking about a conservative system, and therefore this alpha will be recognized as the total energy of the system. Okay. Now if you want to write the solution in terms of W, this W will be then simply equal to WR of R plus W theta of theta plus W phi of phi. Okay. And therefore this equation number 4 now becomes what? When you will find del W by del R, let us see here, then you have to find the partial derivative of this RHS with respect to R. But you can see WR is only function of R. This W theta and W phi are independent of R. They are not explicitly dependent on R. So this del W by del R, that will be simply equal to del W R by del R. Okay. Similarly, when you will find del W by del theta, what will be that? That will be del W theta by del theta, because W theta is function of theta. WR and W phi are independent of R. So their partial derivative with respect to R theta will be 0. Okay. Similarly, this del W by del phi will be equal to del W phi by del phi. So in this expression, in this equation 4, I have replaced all the partial derivatives with respect to R, theta and phi in this way. So this H equation now can be written as 1 over 2m del WR by del R square plus 1 over R square del W theta by del theta square plus 1 over R square sin square theta del W phi by del phi square, and that will be equal to alpha plus k by R. But you have seen that alpha is nothing. This is simply the total energy of the conservative system. So instead of alpha, we have written here E. Okay. So this is your Hj equation. Okay. Now we will simplify this equation to a little bit. Let us see. When you will multiply by this 2m in RHS, the term in LHS will be this much, and that is equal to 2m times E plus k by R. Okay. Now our aim is to separate the variables. Okay. Since there are 3 variables, so in 2 steps we will be able to separate the variables. Now let us see. If you find the value of 1 over R square sin square theta del W phi by del phi square, what will be that? You have to bring the first 2 terms in RHS, and after bringing them in RHS, your result will be 2m times E plus k by R minus del WR by del R whole square minus 1 over R square del W theta by del theta square. Okay. And therefore, you can easily say that del W phi by del phi square equal to R square sin square theta times this much. Okay. Now see this equation number 7 seriously. You can easily see that the RHS of this equation is a function of 2 independent variables. One is R and another is theta. But its LHS is a function of phi. And you know, all these 3 variables, R, theta and phi, are independent variables. Since LHS is a function of phi and RHS is a function of R and theta, and since R, theta and phi are independent variables, so in accordance with the theory of differential equation, you know, in this condition, both sides of this equation must be equal to same constant. Only then for all values of R, theta and phi, this equation will hold. Okay. So let us say that both sides of this equation is equal to a constant, let us say alpha phi square. Okay, alpha phi square. In fact, alpha phi square has been written for taking the positive constant. So you can say that del W phi by del phi square will be equal to alpha phi square. Okay, and therefore del W by del phi will be equal to alpha, which is actually constant, and you know this alpha is actually equal to p phi. Okay, this is equal to p phi, you have seen. And again, the another side, that is RHS of this equation, which I have written it here, that will be also equal to alpha phi square. Okay. Now simplify this equation again a little bit. You can see if you will divide this RHS by this factor sine square theta, and after that if you will bring this uh, second term minus 1 over r square del w theta by del theta square in RHS, what will be your result? Your result will be r square times 2m times e plus k over r minus del w r by del r whole square, and that is equal to this much. Okay, or I have just interchanged the LHS and RHS, so this is nothing else. So this is del w theta by del square plus alpha phi square over sine square theta, and that is equal to 2m r square times e plus k by r minus r square times this much. Again see this equation. Can you say the LHS of this equation is a function of which variable? Definitely you can say this is a function of only theta, while the RHS of this equation is a function of only r. So LHS is a function of theta, RHS is a function of r, and r and theta both are independent variables. Okay, so for all values of r and theta, this equation 9 will hold only when both sides of this equation will be equal to same constant. And now let us consider that constant we denote by the symbol alpha theta square. So we can write this LHS del w theta by del theta square plus alpha phi square sine square theta equal to alpha theta square. And again this RHS is also equated to alpha theta square. Okay. Now let us simplify this second equation a little bit. You can see we can write del wr by del r whole square plus alpha square over r square, okay, equal to 2m times e plus k by r. You can see the algebra. Now you know from this equation you can write del w theta by del theta whole square, that will be alpha theta square minus this much. Okay, so this is this much. But you know del w theta by del theta is what? You have seen that this is nothing, this is simply p theta. So p theta square is equal to this much, and therefore p theta is equal to a square root of alpha theta square minus alpha phi square cosec square theta. Again see this equation 11 and find the value of del wr by del r from here. You can see this del wr by del r, which is equal to what? This is equal to pr, you have seen earlier, and that will be equal to a square root of this much. Okay. Now after getting this result, we can easily find the action variables. Okay, action, how we can find the action variable? Let us see. You know, you have seen earlier that w is equal to wr of r plus w theta of theta plus w phi of phi. Okay, but you have seen that this pr is equal to del wr by del r. Okay, so del wr, or you can say this dwr is equal to pr dr, and if you will integrate it both sides, then this will be integral of pr dr, but integral of dwr, that will be equal to w of r. So instead of w of wr, I have written integral of pr dr. Similarly, instead of w theta, you can write integral of p theta d theta. And for w phi, you can write integral of p phi d phi. Have you understand? Okay. Now, our final aim is to find the frequency of the particle motion moving in this central force field. And for finding frequency, first of all, you have to evaluate the action angle variables. Okay. Here you know that in general you have studied in the previous video that we denote the action variable by the symbol jk. Okay. And you have seen that this jk is defined as integral of pk dqk. We have seen in the previous lecture. Here, actually, corresponding to the three generalized coordinates r, theta and phi, there will be three components of this action variable, and those will be jr, j theta and j phi. And in accordance with this general definition of action variable, you know jr will be defined by the integral for a complete cycle of pr dr. And you know pr is del wr by del r. Okay. So you can also write it at the integral of del wr by del r dr. But you have just seen that what is this del wr by del r or what is this pr. You have just seen del wr by dr. Okay. This is in fact you can find the value of del wr by del r from here, from using equation 11. Okay. So when you will yes, you can see I have obtained this value here in equation 13. So using this equation 13 here, you can see this jr will be integral for a complete cycle 2m times e plus k over r minus alpha theta square over r square whole to the power half dr. Okay. And j theta, this will be defined as p theta integral of p theta d theta for a complete cycle. And you can see this p theta has been defined here. So when you will substitute this, this will be the expression for j theta. And in the similar manner, you can define j phi. And j phi, you know, this is integral for a complete cycle p phi d phi. Okay. And p phi, which is del w phi by del phi, and that is denoted by the symbol alpha phi. Okay. But you know, alpha phi is constant, and therefore you can take it outside of the integral sign. And the limits for integration for the complete cycle for this angle will be 0 to 2 pi. So j phi is equal to del alpha phi integral of d phi from 0 to 2 pi, and that will be simply 2 pi times alpha pi. So one of the action variable j phi has been already evaluated. Now we will actually try to obtain the other two action variable, that is jr and j theta. But for that, if your aim is to obtain the value of j theta, you must have to evaluate this integral defined in equation 16. And for evaluating the integral in equation 16, you should note here that p theta square plus p phi square over sine square theta, this is equal to alpha theta square. Okay. This is equal to alpha theta square. Now, if you will define the Hamiltonian in a plane polar coordinate system, then in a plane polar coordinate system, you know, Hamiltonian is defined as 1 over 2m pr square plus p square over r square minus k over r. Actually, this is the term for kinetic energy. And you know, this PR square over 2m. This is actually the radial part of the kinetic energy or radial kinetic energy. And here this P is the total angular momentum. Don't confuse by this symbol P. Generally we write a small p for momentum, linear momentum. But here this small p has been written for the total angular momentum of the particle. You can say in general, in classical mechanics or in quantum mechanics, we denote the angular momentum by the symbol capital L or J. But you can see in this calculation, L has been written for Lagrangian and J has been written for action variable. That's why I have not used such a symbol for the angular momentum. But instead of that, this total angular momentum has been denoted by the symbol P. When you write PR, P theta, P phi, those are linear momentum. But P denotes the angular moment, total angular momentum. So this is the Hamiltonian of the system in plane polar coordinate system. Now you have seen in the very beginning of this lecture that when a particle moves in a central force field, then Hamiltonian is given by this. I have defined this Hamiltonian in equation 1. You can see H equal to 1 over 2m PR square plus P theta square over R square plus P phi square R square sine square theta minus K over R. Okay. Now let us combine this last two terms inside this square bracket. And after combining it, you can see when you will combine it, you will take 1 over R square as a common factor, and there will be P theta square plus P phi square over sine square theta. But you can see this equation 19 that P theta square plus P phi square over sine square theta is alpha theta square. So when we will use equation 19 in this result, the expression for Hamiltonian will be 1 over 2m PR square plus alpha theta square over R square minus K over R. Now you can see there are two expressions for Hamiltonian. One is defined in this equation number 20 and another is defined in this equation 21. When you will compare both of these results, you can easily see that at the place of the total angular momentum P in this expression, there is alpha theta. So this alpha theta is recognized as the total angular momentum P of the particle. Oh. So in this way, we have identified what is this alpha theta. Alpha theta is total angular momentum. Okay. Now in terms of the linear momentum, you can write the expression for kinetic energy. You know, kinetic energy will be given by half m VR square, okay, plus or take m as common factor, okay, VR square plus v theta square plus v phi square. But you know that this will be half m VR square means r dot square. This is r theta dot square, r square theta dot square, and plus r square sine square theta phi dot square. Okay. But you know m times r dot, that will be PR. M times r theta dot, that will be P theta. So 1 theta dot will remain. Again, m times r square sine square theta times phi dot, that will be equal to P phi. So one of the phi dot remains here. So in this way, you can see the expression for kinetic energy may be written in this way: 1 over 2 PR times r dot plus p theta times theta dot plus p phi times phi dot. Okay. But if you are talking in terms of the plane polar coordinate r and psi, then the expression for kinetic energy can be written as 1 over 2 PR times r dot plus p times psi dot. Here actually r psi are plane polar coordinates. So you can see this p psi dot has been written at the place of p theta times theta dot plus p phi times phi dot. Okay. So you comparing these two results, you can say that p theta times theta dot p phi times phi dot equal to p psi dot. Okay. And from here now you can easily obtain the value of p theta times p theta times theta dot, and this theta dot can be written as d theta by dt, phi dot can be written as d phi by dt, psi dot can be written as d psi by dt. So if you imagine that this dt will cancel in both sides, then this result can be written simply in this manner, that this is p theta d theta equal to p d psi minus p phi d phi. Now we can easily obtain the value of the another action variable, that is j theta. And you know from definition of action variable that j theta is given by integral of p theta d theta, and this integral will be carried for a complete cycle. Okay. So I have encircled this sign of integration. But you can see p theta d theta, this is equal to this much. So let us substitute this here. Now this can be written as integral of p d psi minus integral of p phi d phi. But you can see P is the total angular momentum. And you know, whenever a particle moves in a central force field, its total angular momentum remains conserved. Definitely you have an idea of this. Total angular momentum of a particle moving in a central force field is constant. So it is a constant, and it has been taken outside of the integral. And you also know that this p phi, which is actually equal to alpha phi, that is also a constant. So p phi is also outside of this integral. Now write the limits 0 to 2 pi, and then you can see our result will be 2 pi p minus 2 pi p pi. But you have seen that this p is actually equal to alpha theta, you have seen earlier, and p phi is equal to alpha phi. Okay. And this 2 pi into alpha phi, you have just obtained the value of j phi earlier, and you have seen that j phi is equal to 2 pi alpha phi. We have just obtained the value of j phi here, you can see. Okay. So in this way we have obtained the another action variable j theta, and that j theta is equal to this much. This is 2 pi alpha theta minus j pi. Okay. Now finally we will obtain the action variable jr, and for obtaining this you have seen earlier that this jr is given by integral for a complete cycle a square root of 2m times e plus k over r minus alpha theta over a square over r square dr. But see this equation number 25. From here you can find the value of alpha theta. You can see this 2 pi alpha theta will be j theta plus j phi, and therefore alpha theta will be j theta plus j phi over 2 pi. Now let us substitute this value of alpha theta here in this equation for jr, and therefore Jr will be given by integral for a complete cycle square root of 2m times E plus k over r minus j theta plus j phi whole square over 4 pi square r square. Okay, and you can write this expression in this manner. Actually, this integral is evaluated by residue method. If you have not an idea of integration by residue method, you can watch my video in the playlist Mathematical Physics, Calculus of Residue. I have provided several videos on it. This is actually an independent problem. If I will try to evaluate this integral here using the residue method, that will be a lengthy calculation. So for your examination purpose, it is needed that you must remember this result. For examination, for learning, you can see the residue method, you can watch my video and try to evaluate this integral. Actually, when we obtain the value of this integral using the residue method, then we find that Jr is given by this much, minus j theta plus j phi plus pi k times square root of 2m by a. And therefore you can write Jr plus j theta plus j phi whole square equal to this much. Here I have substituted here a minus sign, or you can write here directly a minus sign. Why? Because we are talking about the motion of a particle in an attractive central force field. And in an attractive central force field, actually the total energy of the particle is negative. So you must put here the minus sign. But the system is conservative, and you know, in case of conservative system, the total energy, that is the sum of the kinetic and potential energy, is equal to Hamiltonian of the system. So this will be equal to H. Okay. Now when you will find the value of frequency, let us say corresponding to R, nu R, you know this will be given by del H by del JR. And what will be that? From this result you can see this will be equal to what? This will be 4 pi square k square m, okay, and divided by Jr plus j theta plus j phi whole cube. Okay. Similarly, if you will find the frequency corresponding to the coordinate theta, that will be nu theta, and that will be del H by del j theta. But when you will find del H by del j theta, result will be same. This will be the result. Okay. So actually the frequencies corresponding to the three coordinates r, theta and phi will be equal. Okay. So Jr, j theta and j phi I have mentioned here are symmetrical in expression alpha theta equal to p. Therefore del H by del Jr, del H by del j theta, del H by del j phi are equal. It means all the frequencies are equal and the motion is completely degenerate. You have an idea of degeneracy. For if for different eigenstate there is the same energy eigenvalue, then that is called actually non-degenerate state. Okay, non-degenerate eigenvalue. Here you can see all the three frequencies are equal, so we say that motion is completely degenerate for a central force field of the form V equal to minus k over r. And therefore the frequency of the Kepler's problem is given by this much. I have already obtained it. Del H by del Jr, del H by del j theta, del H by del j phi. You can see this will be this much. Okay. Now, as you know, time period of the motion is simply the reciprocal of the frequency. So tau if is the time period, then this will be 1 over nu and that will be equal to this much, reciprocal of this equation A. Okay. Now again we will try to find the Kepler's third law of planetary motion. Okay. And for this we have to relate this time period with the semi-major axis of the elliptical orbit. Okay. How we can do it? For this, let us see this equation 28. And from here you can obtain the value of Jr plus J theta plus J phi, and you can see this will be this much. Okay. Now when you will substitute this value of Jr plus J theta plus J phi in this equation B, which defines the time period, then your result will be tau equal to 1 over pi 4 pi square mk square times this much. But you know, if a particle in a central force field is moving in an elliptical orbit whose semi-major axis is A, then actually its total energy is minus k over 2a. So in this case, we will substitute E equal to minus k over 2a in this expression for the time period. And when you will put E equal to minus k over 2a and simplify it, after simplification you will get tau equal to 2 pi root over m by k times a to the power 3 by 2. And you can see this factor 2 pi times root over m by k is a constant factor, and therefore this time period is proportional to 3/2 power of semi-major axis of the elliptic orbit. And this is what? This is nothing. This is simply the Kepler's third law of planetary motion. Okay. So in this way, we have solved the Kepler's problem by using the action angle variable concept. Okay. And I think you have clearly understand. And so watch the video seriously, write down these things in your notebook, revise it, and definitely then you can be able to write the correct answer in your examination. Okay, thank you very much.